Reinforcement learning has again been in the news as of late 24 and early 25 because of the progress that OpenAI have made with their O1 and O3 series of models, and also DeepSeek with their V3 reasoning, the R1 series of models. I'm going to go through some of the theory behind techniques like GRPO, PPO, ORPO, and standard supervised fine-tuning, and I'm going to walk through examples where I improved the performance of a very small model, Llama 1B, on the GSM8K dataset, which is a grade school maths dataset. And I will look at some more complicated datasets afterwards, like the ARC Prize dataset, and maybe others if you want to suggest some, even datasets that are not quantitative or verifiable via mathematical formulas, because that's something I'm going to explain how to improve the reasoning on as well. So without further ado, I'll get started, and you can let me know in the comments if there are other use cases where you would like to see me apply this. Now, unlike other videos where I start with theory, I'm just going to go and start programming right away, because it'll be more intuitive how all of this reinforcement learning works. And along the way, when there are breaks and things are running, I'll take a step out and explain some of the theory. So I'm here in this public repo, Trellis Research One-Click LLMs, and I'm going to find the one-click template for doing fine-tuning. It's this one here, and I'll open that up in RunPod. And I'm going to start with a H100. I'm going to start with this because it's the fastest GPU available. I guess the H200 is maybe a bit faster. By the way, if you're only using one H100, you should probably pick the PCIe. This has got a slower interconnect with other GPUs, but of course, if you're using only one, that doesn't matter. And it's cheaper than the NVL. That's the NVIDIA Link one. So you should go for that one. So this is just the template. It's a CUDA template with PyTorch that allows me to easily run on top of. So I'll click on deploy. And once that has started it up, I'll be able to go to the pod. I've started one up earlier. Go to connect and then SSH and copy here the SSH command. And once that's copied, I can go to VS Code. Let me just get that here. So here's VS Code, and I'm going to click, then connect to a host, add a new SSH host, paste this in. Now in RunPod, you need to have put in a public key to be able to connect like this via SSH, and the key file associated for me is ID RunPod. So I'm going to add that into my SSH configuration, and then I'll connect. Now, the first time you connect, you'll need to clone a GitHub repo into it. The repo I'm going to use today is going to be it's going to be the advanced inference repo. If you go to trellis.com/advanced fine-tuning, you'll be able to find the scripts here. They are private scripts available for purchase. This is the business model that supports the Trellis channel. If you're not in a position to buy these, hopefully you can still follow along at a high level what I'm doing. You'll probably be able to replicate a lot of it by yourself with Cursor, and you can still ask questions, of course, on YouTube, and I'll do my best to answer those. So this is for those who want lifetime access to the fine-tuning repo. It contains many other scripts as well around distillation, full fine-tuning, even scripts around retrieval. Okay, so I'm in VS Code, and I typically would clone the repo here, and you can even clone a repo from GitHub just by typing it in. Granted, you will need access to that repo, and I have done that already, so I'm just going to open up the folder where I already cloned it, and that folder is in Workspace, and then Advanced Fine-Tuning, so I'll click OK. And I'm going to merge this work into the main branch, but for now, it's currently within the ORL branch, so I'm just going to do git switch, and then do ORL. Now, let me just change the color of the screen here, and increase the font sizes a bit, so you can see a little bit more clearly what I'm doing. All right, so I'm in the ORL folder on the ORL branch, and I'm going to start by going to the README just to explain what I'm going to go through. So a few things I want to talk about. First, I want to talk about the data set we're going to do some ORL training on. It's a maths data set. I'll then run inference on it. So I'm going to try and solve these maths problems with a base model. I'm going to solve them with a 1 billion Llama model and see how many we get correct. Now, two things that are important for us to look at are pass at K and majority at K. I'll talk a bit about what each of those mean, and they are going to be very important to understand if you want to do some sampling-based data generation, which will be used to try and improve the model. So I'll show then how to generate a data set by sampling and checking which ones are correct and keeping the correct ones. And then I'll start to show you some of the reinforcement learning type techniques. I'm going to start off just doing supervised fine-tuning. It's the most straightforward, and I think it's not even that much worse than some other techniques. Then I'll move to more reinforcement learning or preference optimization type techniques rather, like ORPO, which is odds ratio preference optimization. Along the way, I'll explain how that is actually very similar to GRPO, which is a group relative policy optimization method that DeepSeek uses. I think there may even be some advantages to not using GRPO. I'll talk about that. Then I'll move to doing multi-step reinforcement. So here I'll just be doing one step of reinforcement learning. So I'll just generate some data, improve the model a bit. Then I'll do it again a second step around. And then later, probably not in this very first video, I'm going to get to verifiable self-correction. This is where we can teach the model to try and correct itself by including phrases like wait or hang on a second, that's not correct, and then getting to the model to regenerate again. And maybe in a future video, I'll discuss some different techniques for tackling the ARC prize. These are very difficult questions for large language models. They're not too bad for humans. And it's O1 and O3 that have significantly improved performance on this and really got people to appreciate the degree of performance improvement that has been achieved with the reasoning models like O1, O3, and now DeepSeek's OR1. So let me talk about GSM-8K first of all. This is a data set, actually I think originally from OpenAI, and you can find a copy of it on Hugging Face. So let's go to it here. And it's a series of grade school maths questions followed by answers. Now, for what we're going to do with reinforcement learning, it is helpful if you have answers that are verifiable mathematically, because this allows you to sample, get the model to create multiple answers, and then you can easily pick out just by doing exact match which ones are correct. But actually, the class of techniques that I'm using today, you could use for any question answer data set. I think it's most useful for difficult questions where the answer requires multiple steps of reasoning to get to. That's really where you want to apply these reinforcement or reasoning type techniques. And actually, because of the way I check the answer, which will be through exact match, but then using a fallback of an LLM as a judge to check the predicted answer versus the ground truth, you actually could use any question answer data set. And you don't even necessarily need to have any chains of thought or reasoning to get to the right answer, but you do need to have the right answer as a ground truth for these methods to work. So we have here a series of questions. There are about 7,500 questions in the training split, and in the test split, there are 1,300. Now, to speed things up, I'm not going to keep running tests on the test set of 1,000. I'm going to only keep running on 100 of these. So I've just got 100 of those 1,300 that I'm using for evaluation. There is noise from run to run of probably a few %, so keep that in mind when you see results. I will be using the full training set because I tried using less and I just didn't get as good results. I tried training with just 100 rows or 1,000 rows, and I did see meaningful improvement using the full training set. So I will be using the full training set when it comes to doing reinforcement learning. Now, to be clear, if you're new to training and test, the whole idea is that we're going to create data sets out of this training set, and we're always going to test on the test set, and we're never going to use the test set in any of our training data. So we're not kind of cheating. And the idea is that because these are questions are different, if we are able to do training in a way that improves the test, it means that in some more general sense, we have improved the model's performance. So first thing I'm going to do is download this data set, and I've got some scripts for doing this. Let's just follow the README here in terms of the order of operations. And before I even do that, I'm going to do some installation. So I'm going to upgrade pip first of all. I'm going to install UV, which is a faster version of pip based on Rust. I'm going to install requirements. And the requirements I have here are going to include a few things: datasets, which is a Hugging Face library for managing the dataset, requests, which is for making requests, Light LLM. So I'm going to use Light LLM. It's a wrapper for basically any private or OpenAI style API. And you can make a call to Light LLM and have your Gemini API key in the background. You can make a call in OpenAI style format, and it will handle making sure that you can just use one format for calling the API, but it will hit many APIs. I actually have a video on this. I recommend using it instead of writing code that's able to handle all the different APIs. Okay, these are the main libraries I want to highlight. So I've run that installation. And next I'm going to install sglang. So sglang is like VLLM. It's quite similar, and it's going to allow us to run inference on this H100 GPU and generate samples. Now, sglang, in my experience, in pretty much every case, has been significantly faster for batch generation. If you're just generating one answer at a time, it's probably similar to VLLM. VLLM probably has got some advantages on specific things. Maybe if you're used to how it does structured generation, although sglang does that now. But sglang, in my experience, is a lot faster when you've got large batches. And we're going to want to speed up all these tests as much as we can. So I'm going to use sglang. So with that, I'm going to create an environment variables file. You can see here in sample.env, the one that you need, you don't need this one, is a Gemini API key. And the reason is because I'm going to check the correctness of the answers. So when I check the answer given by a language model with what the ground truth is, here it's 72, I'm going to, as a backup, use Gemini to compare the answers if there is no exact match. And you'll see that this actually does catch some cases where exact match fails. I'll show you why it fails. It's about 1% of the cases, so I wouldn't say it's too meaningful. You can probably get away with just exact match, but I've put in that backup. And the further benefit of using checking with Gemini is that it's also going to allow us to do non-numeric question answer data sets. Okay, so I've got Light LLM set up. I've got my inference library installed. And now I'm going to download that data set. Now, you can download it using this script with a few different arguments here. You can specify the split of either test or train. And then you can also specify how many rows. So you'll see here, I download 100 rows of the test split because that's the limited amount we're going to use for evaluation. And then I typically download the full amount here. It's, I think, 7,473. So I download the full training split. And if you want to download it in full, actually, you can also just use -1. That will give you the full training split or the full test split. Now let's quickly take a look at the script. It's nothing too special. It's using Hugging Face datasets to load this dataset here. It checks for the -1 if you want to load everything. And it's loading the examples in two parts, question and answer, which is very straightforward. And that's pretty much it. We're going to have a data set with a question column and an answer column. And we're going to have them saved. So you can see here, here's a test split of 16, and we've got them all here. Now, why did I download a test split of 16? Because when I do fine tuning or reinforcement learning or whatever you want to call it, I'm going to have a training set, but I also will want to create an evaluation set, which is an independent set I'll be able to track the loss on. This is important because it tells you if you're overfitting. And generally, during your training or reinforcement learning, if your evaluation loss is not going down, or worse, if it's going up, that's a strong sign that your process is not really working. So that's why I always like to have an evaluation set, and I've just made a small one. You could run with a bigger one. You could use the full test set of 1,000 examples, but that's going to slow your training because now every time you run eval, it's going to have to run 1,000 samples, whereas I just want to run 16. Okay, so there's also the option to download the ARC dataset. I'm not going to talk about this right now. This is a more complicated dataset. You also need to do a bit of pre-processing on it because of how the samples are laid out. So I'll plan to talk about that a little bit later, but you're welcome if you've access here to the repo to dig a bit more in yourself. Next up, I'm going to talk about answer checkers. So the idea is we're going to feed into the LLM. And by the way, we're going to feed it into Llama 3.21b instruct, which is a small model. The reason for using a small model is because this benchmark here has been largely saturated by bigger models. Even this model raw is quite good. It's going to score, if you allow it to sample 8 times, it's going to score above 80%. If you allow it to sample once, it's probably going to score about 60%. But if you go up already to the 3B, it's going to be up probably towards the 90s. And so there's not really much room for improvement by doing reinforcement learning. Now, why not do a harder data set from the start like ARC? Well, you could, but the thing is this model is just going to be too weak. And so there won't be enough correct answers that we'll be able to bootstrap our way to getting better performance. Not saying bootstrapping is trivial for bigger models, just saying we definitely will have a tough time if we're using this model to try and solve ARC. Also not saying that's impossible. but explaining why I made the decision I did. So we're going to run this model and we're going to pass in each question asynchronously. So we're going to hit the LLM endpoint with many requests just to get speed. And for each question we pass in, like this question here about Natalia, we're going to get back an answer. And then we're going to grade the answer. So we need to have a way to grade the answer. And that's what I'm going to talk about now, which is the answer checker. Now let's take a look at the answer checker. It's in utils, and you'll notice I've one for arc. Arc, you can check against a grid of numbers. That's how you check the answer. I'll talk about that another time. But for this GSMK, you're basically 8K, you're basically just checking that the answer matches the number here after the 4 hash symbols. So a typical approach is to take this string of text, extract the number after here, and then try to extract it from the answer your LLM generates and compare those two via exact match. And so that's exactly what we do. But there's a few other things that I'm going to mention as well. So let's start with this function here, which is check answer async, which is an asynchronous way, which means we can parallelize it to check the answer's truth. And it's going to take in a few things. It will take in the question, the model's answer, this is the prediction, the ground truth answer, which I just showed you here on the repo, and then the maximum number of retries. If we have to resort to the Gemini API and we fail to hit it for some reason, we're going to retry. Now, this might seem like a lot of detail, but you do need to implement this because otherwise, say Gemini fails, it doesn't give back a proper verdict on whether your answer is right. It could be marked false, even though it's correct. So you need to have confidence that your answer checker is actually working robustly. Okay, so with the question coming in and the model answer coming in and the ground truth, we're first going to check. So here's the first kind of wild card, because I haven't said this yet. We're first going to check the answer has got valid think tags, which means that when the answer comes back, we're going to expect that the answer is formatted like this. It should be formatted with think, and then, oh, I think 2 plus 2 should be 4. And then it should have a closing think tag like this, and something that says the answer is 4. Okay, so this is the answer we want. And you can see we want the answers to converge towards having this thinking in front, which is the whole thing everybody's talking about nowadays. So we're going to require this, or we're going to allow it to be required that the answer has these think tags. And if it does have the think tags, we're actually going to strip this part out and just do answer checking on the part after the think tags. So we're going to only do answer checking on this part. Now, you might be asking, how are we going to ensure that the model responds like this? And we're going to do it in two ways. One is we're going to prompt it to do this. And the second way is we're going to achieve this through the reinforcement learning or supervised fine-tuning steps. So we're going to basically incentivize the model to respond in this format. And the main way we're going to do that is by creating data that is only included in our training data set if it's properly formatted like this. Okay. So we have a function here to check the answer. And the first thing we do is check the answer has valid think tags. And I'll talk about this in a second, but we do want the option to enforce this or not. Basically, we always want to enforce the think tags if we're creating data that's going to be used for training, because we want the data to be perfect. But we generally do not want to enforce it if we just want a sense of whether the model is getting things right or wrong, because the model might get the answer right even if it doesn't have the think tags, in which case, I mean, the answer is right. It's just that it hasn't provided the right format. You come back to that if you're still a bit confused a bit later. The next step is we actually take out everything between the think tags. Why do I do that? Because if the answer eventually goes to Gemini to be asked if it's correct, you don't want to send a massive chunk of thinking because it's going to increase the chances of Gemini being confused. So you want to clean that out and just give in the answer. And then we take the cleaned model answer and we extract the number from it, or at least we try to extract the number from it. And the way we do that is just through regular expressions. So we look for this quadruple hash or pound if you're in the US, and we basically grab the number. And this fails for some interesting reasons sometimes in a small percentage of cases. And in those cases, or rather in any case where we don't get an exact match, so it could just be because the model answer is wrong, we then resort to sending the answer to Gemini. If the answer, on the other hand, is an exact match, we mark the question as correct, we record the explanation as being an exact numerical match, and we record the extracted answer and the extracted ground truth. We also record which method was used for checking. But if it fails, we move to the Gemini checker. And what does the Gemini checker look like? You're an expert math answer checker, focus only on the numerical answer, ignore any reasoning steps. So this is also a subtle point. We're saying mark the answer correct if the final number is correct, even if the reasoning is wrong. Now you might think, oh, wouldn't it be nice? We can just ask Gemini to check the reasoning too. The problem with that is Gemini won't be robust, because ultimately we'll want to tackle questions that are harder than what Gemini, or at least this cheap Gemini model, is capable of. So it's actually better just to get it to only focus on the answer, because we know that's going to be a systematic way of determining whether it's right or not. I should note that for more difficult questions, it's very difficult to fluke the answer. And if it's difficult to fluke the answer, it means it's a lot less likely that the logic on the way up is also going to be wrong. I won't say that's true in all the cases, but something we're thinking of. So here's the prompt that goes to Gemini. You're an expert. We pass in the question and the cleaned answer. No thinking tags, because that would make the context really long. And we pass in the ground truth. By the way, if your question is really long, you may not want to pass it in, because again, it's going to confuse the context. So you may just want to pass in these two things. But for these questions and for ARC, it's fine to pass it all in. In some ways, it provides more context. You could argue it's helpful. You really should ablate which one works better. And then we pass in the extracted numerical answers. So the model's final answer, which, by the way, may be not extracted exactly correctly. And then the ground truth answer here. And then we ask the assistant to tell us whether the answer is correct or not by giving a brief description and assessment, and then giving a verdict of either correct or incorrect. And then we have some retry logic, allowing for up to 3 retries. And if it fails, those 3 retries. And by the way, I'm trying to make sure it stays below the rate limit for hitting the Gemini API as well. But if it fails all of those, it will just be marked wrong. But it will flag to us in a summary report at the end how many fully failed, like 3 times Gemini calls there were. So we should see if that's happening or not. All right, so that's the answer checker. And with that, we're ready to run a few scripts. So the first scripts to run are evidently to download the dataset. The dataset I care most about to get started is this 100 examples from the test set. And I want to evaluate performance on that using my Llama 1B model. So I've downloaded that. I've got it here, GSM8K100. And now I'm going to run a script to run inference. Now I've got some basic, simple and batch inference scripts here. But what I want to do is run a more complex script that allows us to sample, because I want to measure not just if we try once, but if we try multiple times. And the reason for this is because if you set temperature non-zero, you will get a range of answers from the same LLM, and some of them, maybe one of them will be correct, and maybe one won't. And this gives you oscillation in your results. So if you just test what's called pass at 1, whereas you only allow one answer per question, you're not going to get a full statistical picture of how correct the model is. So to get a fuller picture, we're going to sample 8 times per question, and we're going to record 2 things. One is the pass at 8, which means did we get it correct at least once out of every 8? And the other is called maj at 8, which means majority at 8, and that means did we get the majority correct out of 8? Now, I take a strict definition of the majority of 8, which literally means you need to have more than 50%. So if it's 8, you need to get at least 5 correct for majority at 8 to register for that question. Now, the reason this is relevant is because if in a real question where you don't know the ground truth, if you know that you're able to achieve majority of 8 correctness, that means you can run a question 8 times and you can take the 5 answers that are the same, at least 5, and you will know that that is the correct answer. If you based your majority based on 3, that wouldn't be robust, because you could have 3 answers that say A, 3 answers that say B, and 2 answers that say C, and you would have no way to know just by looking at the data whether it's A or B that's correct. So yeah, that's why I take a strict definition of majority at 8. So I'm going to run inference now. And I'm going to run this sampling batch inference script, which I'll show you in a moment. I'm going to run it on the GSM8K dataset. I'm specifically going to run it on the test split with 100 samples. I'm going to run the model of unsloth, and I'm going to sample 8 times. So that's what I'm going to do here. And why don't I just run it? Why don't I just run it here? I need to move into the ORL folder first. I'm going to run it because this will give us a sense of how it runs, and then I'll show you the script. So what's happening here is the model is being loaded into SGLang. The shards are loaded, and you can see the endpoint is now set up here. It's running on port 8000. And actually, the examples are all now running. So it's moving a bit too fast, but you can see when, you can't see, when there's a response received, it's then being checked with the exact match. Then it's being checked by Gemini if the answer was not an exact match, and then the verdict is being passed. And this is being done 8 times. And you can see here a summary. So we have 8 samples per question. I'll talk about weight functionality in a later part of this video or the next. We attempted 100 questions. We got 79 questions where at least one was correct out of 8. 31 questions where a majority, which means 5 or more, were correct. And that took us 509 calls. There were 509 successful calls. Why, by the way, isn't there 800 calls? Because we obviously matched, we got the exact match in those other cases, so we didn't need Gemini. And you can see there were no failed calls, so that's good. And there were some cases where the exact match failed, but it was marked correct by Gemini. And this happened in just under 1% of the cases, as I said. Let's take a quick look at that. I know I'm getting into nitty gritty here, but these things make a difference if you want reproducibility. Let's go to exact match disagreements. And you can see here, it's a question about Claire eating or making an egg omelette. We have a model answer. And the answer here is Claire will eat 7 dozen of eggs in 4 weeks. And you can already see why the exact match is failing, because the exact match is pulling out the last number here. But actually the answer is the 7. So you can see that the model's final answer is 7 and the ground truth is 7. So actually these answers do match. So even though the extracted answer was wrong, it was good that we had Gemini there as a backup. Okay, let me see if there's anything else I got to say. You'll notice here the length of responses. So the length here is 544 characters versus for incorrect responses, they are longer. This is often true because you get repetition patterns, particularly when we haven't yet tuned the format of the response. We tend to get longer bad responses that are just repetition. And it's not as though they're all long. It's just probably there's a few that are quite long. But the reason why you want to track length is because if you look at the DeepSeek paper, and let's just go to it now. Let's go to DeepSeek R1 paper. Key things that is found with reinforcement learning in DeepSeek is that as they train for more steps, they find that the average length of the response goes up. And this is the LLM kind of backtracking or sampling, resampling, trying new ideas. And they find that doing reinforcement learning, they're able to extend the length of the correct responses. Not as though that's a direct goal. It's not written into their logic, but it's something that emerges and is quite interesting. So that's why I'm also printing it, and that's why I'm interested. And we're going to track it because you're going to see some interesting things happening to the length of the correct responses. All right, so before I run any more scripts, let's do a few things. Let's just take these results here and use them as a baseline. So let's save them here at the very bottom of this. Let's save them under the baseline performance. You can see I ran it earlier. You can see this is actually the same run and it highlights the difference you might get just to noise. So you can see I got 78% before, I got 79 now. I got 28 before, I got 31. So you can see this is about the level of noise if you just rerun the same thing. And so if we want to see an improvement, we got to see an improvement of probably about 5 to 10% to say statistically that we're actually improving on this baseline. Now, just 1 or 2 more comments. If we find a way through reinforcement learning to improve the pass at 8, which means the model is able to reach at least one correct answer more often, this means we've somehow improved the model's capabilities. Whereas, well, we've improved the model's reach. It's able to reach some new answers that it wasn't able to reach. Whereas if we improve the majority at 8, that just means we're making it more consistently give the right answer. So in order to improve majority at 8, it's not necessary. It might already have been able to find the answer 1 out of 8 times, but it's now able to find it 3 out of 8 times. So there's this kind of conceptual difference between improving a model's pass at 8 and majority at 8. And you could, or some people have argued, there are cases where you'll find big improvements in majority at 8, but you're not improving the pass at 8. And obviously, if you can't improve the pass at 8, you're always going to be having a ceiling on the number you can get correct. So kind of the holy grail of reinforcement learning is being able to improve not just the majority at 8, but also the pass at 8 or pass at 64 or whatever. And usually people will say it's logarithmic. So if I sample this 64 times, I might see an increase that's linear with the log of that number of samples. Now, you probably saturate at some point. Okay, so let's quickly look at the script here around the batch inference. I'll explain some of the nuances here. And then we're going to start moving towards trying to improve this performance. So we're going to see if we can get a better performance on it. So here's the script on the batch inference. And the best place to start is usually the main function. So first thing we do is, well, we check if we're going to be running GSM8K or else ARC. And then that allows us to grab the dataset name. There are 2 arguments I allow, which I'll talk about. One I'll talk about later. This is the wait tag here. This is encouraging the model to kind of wait and reflect. And then there's the think tags argument. Now, think tags argument, we've actually talked about briefly, but let me explain it now. It'll make more sense. When I evaluate the correctness of answers, I have a choice of whether to just check if the answer is correct or to check whether both the answer is correct and the think tags are included. And to do that, I include the argument think tags. I just include that flag within my command, think tags actually. And when I include that flag, it forces for an answer to be marked correct to also have the thinking tag, the thinking and the closing tag. And the reason this is good is because if I want to generate a data set to train on, I might want to train on data that's not just getting the right answer, but also has got this formatting. So this is my way of enforcing the think tags, and it's a way to enforce it using just supervised fine-tuning. You can also enforce it using something like GRPO, group relative policy optimization, and you can set up a reward that will reward the model when it has the right format. But actually, I think this is a more efficient and cleaner way to do it. And I'll talk more about those kind of trade-offs a bit later. So here we've got, we're just setting up the results directory for where we want to save things. We'll open up the data set. This is for a GSM8K, so we're interested in this. We'll read in the data and we're going to start the server here for a specific model. So we can look at the start server function later. It's just an sglang process. Let me show the full screen here. And next we're going to start processing the questions. So we'll have to look at the process questions function, but this gives us back results. And those results then we're able to use to calculate the pass at K. It just checks if at least one is correct. And then majority count, which is calculated using the majority count from the results. So basically the results will report out the pass at K for each question and also the majority at K for each question. And here we're just accumulating over the 100 questions to get the percentage that were correct on a pass at K basis or a majority at K basis. And then based on that, we print out the data I just showed you, which includes data around the final results and also around the Gemini stats that's hitting the API. So quickly, let's look at process questions. Here we have a function that takes in a data set, the model name, the results directory, whether it's ARC or GSM8K, and also whether or not to check for thinking tags. What it's going to do is set up, first of all, some of our rate limiters. We need a rate limiter for hitting sglang. sglang automatically does batching, but ultimately if you hit sglang with 7,000 different queries at the same time, then many of them are going to time out. So even though it handles batching, you still need to have some limit on how many concurrent requests you're going to send to it. Also for Gemini, if you hit the rate limit, I can't remember what it is, maybe 20 or 100 per minute, you're going to get issues. So we need to set up an asynchronous process using semaphore, using some rate limits. We also need to initialize our answer checker. That's just what I showed earlier, before we can move to processing a single question. So to process the questions, we're not going to be interested in the ARC section. We're going to be interested in the other case for GSM 8K. And here we're going to get a model answer by passing in a session, the example, the model name, SGLang, the number of samples we want, which will be 8. And then this thing I'll talk about later about whether we enable weight or not. And then when we get the answers back, we're going to check the result. We're going to start recording the stats. We'll ignore this part here around enabling the weight because we'll come back to it. And then we'll just append the results here so that they can be read out later on. Now let's, by the way, there'll also be calculate metrics. This is where we're going to calculate the pass at K and also the majority at K. So you can see those stats are being calculated here. So let's go back. I don't want to dive too deep here, but let's go into at least the get model answer and see how that works. So the get model answer is going to take in a system prompt, either for the ARC questions or for the GSM 8K question, which I do want to look at. It's going to pass in a messages array, which will have the system prompt and the question. And then it's going to pass in this data that's needed for inference. So the model name, these are all things that look standard that you pass into an OpenAI style endpoint. We're going to allow max tokens of 8,000. If you kept doing many trainings, you might get over that and need to increase it. And with that, we're going to make our call to SGLang using the rate limiting and get back our results. So this is basically our wrapper. That's not so much wrapper, but it's what calls SGLang, which is the server that we're running on port 8000. Now let's take a quick look at the prompt. The prompt, rather the system message, is included in the configuration file. And you can see it here. Your helpful maths assistant, solve step by step using the following format. Put your reasoning inside think tags and end your reasoning, provide the numerical answer. And you can see here I give a little example followed by the answer. And I even encourage it to use this quadruple hash sign here. And there's a separate prompt that will be used for ARC. So this is roughly speaking what the sampling batch looks like. It's taking multiple samples off an SGLang server. It's requesting via that prompt I showed you the answer to have thinking tags, which generally is followed even with Llama 1B, interestingly, but it's not followed in some cases. So you will find some answers are going to be rejected if we force thinking tags to be correct. They'll be marked as wrong because they just don't follow it. So with all of that, we now have our baseline performance and we're ready to start doing some reinforcement learning. But there's one more ablation I just want to show. I won't actually do it. I'll just tell you the results. But if you run with the think tags, so previously I ran like this. If I decide to add in here think tags, this means I'm enforcing think tags for an answer to be correct. It's going to reduce the number that are correct. So you can see here, the pass at 8 goes down to maybe 65 and the majority at 8 goes down to 19%. And what that means is that there are answers here, roughly 10% in the case of pass at 8 or 20% in majority of 8, that are wrong because they're giving the wrong format, but the answer is still correct. And this, you would expect this gap to narrow as we do fine-tuning, as we do reinforcement learning, because the model should be responding using the think tags correctly. And so we should be starting to see results that actually match, regardless of whether we require the think tags to be there for the answer to be correct. So if that doesn't make sense, you might get it a bit later on, but it is a subtle nuance as to whether you should mark an answer correct if it's got the right format or not. And my argument is you should mark it as correct if you should require the tags to be there if you're generating a data set, but you should not require the tags to be there if you're just testing out the performance, which is what I've done here. So this here, to be clear, does not require think tags to be marked correct, just to be clear. Okay, so next we're going to move to try and improve the performance. And we're going to do that by running some supervised fine-tuning. So we need a data set. And the way we're going to get a data set is by taking some correct answers from the training set. So there are a few steps here. I need to first of all run inference on the data set with the base model. And I'll do that using the sampling script, using the GSM-8K, using the base model, but I'm going to use the training data set. So here I want to use GSM-8K, and can I remember the name of the file? It's actually easier if I just backtrack here, put in train, and that. So I want to generate a training set using the 7,000 training questions. And I also want to enforce the think tags. So I only want answers to be marked correct if they have the think tags. And I'm going to run this. Now, I've run this script earlier. It takes more time. It doesn't take that long, maybe 15 minutes. But it's basically got to run 7,000 questions and sample them 8 times. And when that is done, you're going to have more than 7,000 questions because, well, you may not necessarily, it's going to depend on how many you get correct. But I can tell you that Llama, it does get many more than 7,000 questions correct if you run 7,008 times. So you have a data set. And once you have that data set, you can filter out the correct answers and use those for supervised fine-tuning. So that's what we're going to do. Now, there's a more complex approach, which is now moving into preference fine-tuning, where you could actually pick out pairs of correct and incorrect answers. And there are different ways you can pair them. You could allow each correct answer to be in exactly one pair, or you could do all of the pair options. So you could take, for a given question, there are going to be 8 answers. If you have 4 correct and 4 incorrect, each of the 4 correct can be paired with each of the 4 incorrect. That's 4. And you've got that 4 times. So you'd actually have 16 possible pairs in that case. So I call that complete pairs and restricted pairs. Now, the risk with the complete pairs is you're kind of overtraining. The risk with the restricted pairs is maybe you don't have enough data. We'll get to that later when I talk about preference fine-tuning, but we're going to keep things simple for now. So we're just going to focus on using the correct answers. But nonetheless, just for dataset formatting, I'm going to anyway create the pairs so they're ready. And then I'm going to just use the correct pairs. So in my training script, I'm going to just grab out the correct answers. So the way I'll create these ORPO pairs is by running a script called create ORPO pairs on the GSM-8K script. And the results directory I want to pull from is going to be the one where I just created the training samples. So I want to pull from this directory here, which has 7,473. Well, it was generated using that. And you can see the underscore TT means that I'm enforcing the thinking tags. So it looks like I have got the right, I've got the right results folder here. And the pairing mode, I'm going to use restricted. There's already quite a lot of data, so that should be sufficient. So let's run that, and you'll see here what this looks like. So we've created 14,000 pairs. We've skipped 1,000 of the 7,000 questions because there were no valid pairs. And the reason there are no valid pairs is because if you get 0 out of 8 correct, there is no correct answer that you can do fine-tuning on. There is no correct answer you can do ORPO fine-tuning on either. So I've saved those. And now I have, just as an example, you can see a pair here. So this is the model. The system prompt is as before. And the question is here about John and pills. And the chosen answer, you can see it's got the correct think tags and it's got the correct answer. I don't actually know it's the correct answer here because I haven't printed the ground truth, but it is the correct answer because that's what's being checked in the background. And the rejected answer, the reason this answer is rejected is actually because the opening think tag is incorrect. It's got a / here. But other than that, the answer is correct. So this is an example where by using this pair later with ORPO training, we're going to try shift the probabilities of the model towards answers that have think tags and away from ones that have this incorrect think tag here. Now, sorry if I'm confusing a bit by talking about ORPO, because we're just going to focus on the chosen answers for now with supervised fine-tuning. We're going to do cross-entropy loss just on the correct answers and see how that does for us. Now, very quickly, I'll show the create ORPO pairs script. I'll look at the main function down here. And it basically parses the arguments, and then it extracts the model name from the results directory and creates pairs. This is the key function we need to look at. And the way we create pairs is we pull out the question first of all, and then we split the samples into correct and incorrect. And we only we will skip this if we can't create pairs. So if there are no correct samples, there are no pairs, which is what I said earlier from the logs. And then depending on whether we want complete pairs, where we do it for every C and every I, or we just want restricted pairs, which we'll call another function and just find the unique pairs. By the way, if there's only one right answer and 7 wrong, there's still only one possible pair. It'll just pick a random one of the 7. If there's 7 right and 1 wrong, there will also only be one pair, because there'll be 1 right and then there'll be 1 wrong. Sorry, one of the 7 randomly chosen right and then the one that's wrong. And so this is how the answers are collated here. Okay, so we've covered how to create the ORPO pairs. And the next step here, I'll just call it step 3, is to train the model. And we're just going to train with supervised fine-tuning. And we're going to do that using a script I've prepared that is based on unsloth. Now, I always recommend using unsloth if you can. It will only work on one GPU, but that's what we're doing. It's usually twice as fast as using transformers, but it only supports specific models. So for Llama, it supports them. If you wanted to run DeepSeek Lite Coder V2, which is a model I like, it's 2 billion parameters activated, but it's an MOE, so it's actually much bigger. It will not run using unsloth, so you have to use transformers. There is a transformer script here too, so you could just run that as well. It takes the same arguments, and I'll go through the script in a moment. But basically, the way we're going to train is on a GSM8K dataset. We're going to train using the ORPO pairs in this directory, and you'll see because I ran that create ORPO pairs script, you'll now see there are ORPO pairs present, and there are a large number. Let's open anyway. So here, each pair has got a model, a system prompt. So the question is there, and then there's a chosen answer, and then there should be a rejected answer. Yeah. So these are the ORPO pairs. And we need an eval data set, which reminds me, so we need to create this as well using ORPO pairs. So we need to run inference, and we need to do it on the test split. So we're just going to run it on a small test split. And again, this is going to help us check overfitting by looking at the eval loss during training. So we're going to run this script here, and I'll actually run it live now because it'll be quick to run. And we'll also need to run create ORPO pairs to set up our data for that small eval split. Now it should be pretty fast here because we're just running 16 times 8 to create this small eval data set. There we go, set up on port 8000. And here we go with the results. So, I mean, I'm not going to use this really for benchmarking. It's not statistically significant enough. It's intended to be quick, a quick and dirty indicator later during training. But yeah, it got 80% correct, pass at 8. It got 1 out of 16 correct. Otherwise, in the majority at 8, not that that's of much consequence. We'll now create the ORPO pairs. And it's created 23 pairs and skipped 3 questions, which makes sense. So now we actually have that data, and it should be available in the folder over here. If we just look at the 16, you can see that the ORPO pairs are now ready here. So let's now move to running the training using that training set and the eval set. We're going to set run number 1, because the whole idea here is we're going to train with this data that's very clean. It's got thinking tags. It's got the correct answers. We're going to train with this, and then we're going to see if performance improved. If performance improved, it means we're able to generate a bigger data set next time because we're going to have more correct answers. So we're going to be able to kind of get a flywheel going and see if we can work our way up the ladder of performance. And that's the model name there. So let's just run the training, and then I'll describe the training script. Now, before running the training, we do need to run some more installations, which you can find in the training section down here. So the training installs depend on whether you want to use unsloth or transformers. And I'm going to use unsloth, so I'll install this here. So let's run all of that. And when that's done, we should be able to start to run our training script. Okay, so we've installed everything, including flash attention, which is possible because we're not on a Collab T4, which doesn't support it. And so we can run training. And once we're done with training, we're going to put the results here. And well, we'll have to actually then test it. So we'll have to run a test using something like Python. Let's put in bash here. We'll have to run the sampling script, but we're going to run it on the fine-tuned model, which will actually be set up to have this tag SFT1 for the first SFT run. And we're going to run it on 8 samples. And notice that we're not going to put in the thinking tags because it's not cheating. That would make it stricter. But we actually just want to know how many it gets right. If it doesn't get the format right, it's still getting them right. That's how we tested the baseline. So that's how we want to test now. And we want to say it gives these results. And we're basically trying to see, are we able to improve on the baseline here of roughly 79% and roughly 30% in majority at K. So actually I realized I ran ORPO first because I used the autocomplete here without being careful. And the correct script I want to run is SFT. So let's run that. I could have let ORPO go, but ORPO takes longer because it has to include the chosen and the rejected. So effectively, you've got a longer sequence length. So I'm going to rerun, and this should run a lot faster. And let's see if it does print the chosen and rejected response. No, it just shows the answer, and then it shows the response here, and they're just concatenated, which is exactly what you'd expect. So we're getting everything prepared correctly. You can see it's mapping the data set, 14,000 examples. And it's mapping then 23 examples for the eval data set. And this here is fairly fast. It's going to take probably just a few minutes. So I can now go over to TensorBoard. I've run TensorBoard -- logdir and then logs. And I have that up and running right here. And the run we're on should be indicated with ORPO, with SFT rather, and then the number of the run. So let's see if I can find that. So here it is, llama 3.2 instruct _ SFT _1. And I need to refresh. And here we go. So you can see here, we're moving to the training. And the grad norm is sufficiently low. That's a good sign. The training loss is going down, also a good sign. And we want to wait and see now if our eval loss is falling. It's still probably early in the training. We can check here. Yeah, we've got 1 eval loss, which looks good. And we're hoping that goes down a bit more. Now, while that's running, let me briefly describe how this SFT script is running. And here we go. So we look at the main portion. And what the SFT script does is read in the dataset from ORPO pairs. Of course, we're only going to look at the questions and the chosen responses. We're not going to look at the rejected responses. We load the tokenizer. We load the system prompt for GSM8K. If it's GSM8K, which it is, that's what we're looking at. And then we calculate the maximum sequence length of the dataset using the tokenizer and the system prompt. And once we have that, it allows us to set this max sequence length parameter within, which is going to be used later when we're configuring the training. Now, optionally, you could run with quantization if you comment that in here, but I'm not doing that because I want to keep quality. I'm running in bfloat16. I'm running with device map equals auto. It'll be dispatched to the GPU. And here I'm going to apply LoRa to target modules. Now, this is probably a bit unnecessary setting up the function here. It's easier probably just to hard code them. But you can see that for llama models, I'm training the attention and I'm training here the MLP, so the feed forward layers as well. If I'm training DeepSeek, one of the models, it's a mixture of experts, so it's not recommended to train the MLP in that case because they can be sparse. Okay, so once the model is loaded, I've set up my LoRa. I've got the rank of 64. I'm using a high rank because I want to have good kind of precision in doing the fine tuning. The LoRa alpha, I've set to 32. And you would set it larger if you had a larger model with a larger hidden dimension. It should roughly be the square root of the hidden dimension. And I apply getPEFT model, which is a function from the PEFT library, in order to generate these adapters that we're going to train instead of training the base weights. And next I format the data set. So basically I've got the model loaded with LoRa, and now I format the data set. And you can see here how my data set is formatted. Basically I set up these messages with the system prompt and the question. I set up the proper template using apply chat template, but not tokenizing. So I'm not going to tokenize, but I will generate the template. And then I append onto that prompt. So this prompt here, which has got the system and user message, I append on basically the chosen response and then the end of sequence token. And you need the end of sequence token there because you want to train the model to actually finish when it should finish. So with the formatting of the prompt done, I'm ready to set up some of my parameters here for evaluation. Basically, I need to format the evaluation dataset too. So I'm doing the same thing there. And this is where I print out what that looks like, just to check that it looks all good. Then I'm ready to move on to training arguments. So I'm going to train with a batch size of 4. Actually, you could train with much larger as you move to later steps of the reinforcement learning, because the model actually starts generating shorter, more concise answers initially, because it gets rid of repetition problems or bad formatting problems. So yeah, this is not something I would have guessed, but initially the length of responses gets shorter, in which case I can pack in more batches because they are shorter. And then we'll see how the response length goes as we go through multiple steps. But I have my virtual batch size of 32, which is 8 times 4. So I'm basically changing gradient accumulation such that the product division, the batch size, is equal to 34. Now I'm training for 1 epoch. This is quite a low learning rate, but I did ablate different learning rates and I found that this worked well. Usually for a 1 billion model, you'd use something like maybe 5e minus 4. So this is quite small. I'm using BrainFlow at 16. I'm logging every 10% of the steps. I'm evaluating every 20% of the steps. I'm using gradient checkpointing. Actually, I can use reentrancy here, which will speed things up. And that is typically recommended if you can. It gives issues sometimes with Qwen or DeepSeek models, but it is actually better to use that. So I'll switch that for now. I had it switched because I was testing with DeepSeek. And then you can run the trainer, or rather set up the trainer with the data set, the eval set, the tokenizer, and you're ready to start training. And once the training is done, we'll save the model, actually merge the model and then save it, and save the tokenizer as well. Now, I realize I've just run through the SFT script for transformers. The unslop script is pretty much the same. It looks a tiny bit different when you're loading the model. You can see that we don't use auto model for causal. We actually load the model and tokenizer using a fast language model right here. The only other difference for the unslot script is that, and let's check actually what my batch size is. Yeah, you can see actually I've used a batch size of 32 and it seems like I'm getting away with that. Yeah, I got away with it even though my max sequence length was high, just because SFT requires a lot less memory than. But unslot, the other difference is how it saves the model. There's a single function that you can use to save and merge instead of the 2 separate functions I showed you here if you're using transformers. Okay, so it looks like we have got this in good shape. Let's take a look at TensorBoard to see how we're doing. I'll refresh and let's just kind of zoom out a little. So you can see here, the grad norm, you know, it does go a little crazy here, but it is a small sample size for our eval, so I wouldn't worry too much. The grad norm on the the grad norm is for the training set. So yeah, it's not too bad. That comment set aside, that's incorrect what I just said about the eval size. Grad norm is only relevant for the training set. You can see the training loss is falling. It's not falling by a huge amount though. Initially it is, but then not by too much. And the eval loss, it's falling a bit, but not all that fast, I would say. Certainly feels like it's asymptoting. By the way, I'm using a constant learning rate. So this kind of shows that probably my learning rate is fine because we're not going to get much more improvement beyond this. So let's go back here. And while I'm at it, let's just save any updates that we've made. And time now to run and see if we actually get better performance after doing all this. And we're going to run on the 16 samples. But we're now going to use the model that has been merged and saved. So if we check up here, you can see there's a model saved right here. And yeah, it's been merged. So we're going to run that now. And we're not going to run it with think tags because we want to give it the chance to get things correct even with the wrong format. So let's run. And it looks like I didn't pass the correct data set. So let's check. And the file I want to run should be in results. And I don't think that's the correct one. I had the wrong file name there because the data set we're trying to run is this GSM8K test 100 rows. And let's see how things go. And looks like we have 76%, at least one correct. And we have majority of 8 goes up to 36%. And let's see how that compares back to our baseline. So the baseline results here, 78%, and we've 28%. So I'd have to run this again. In fact, I can just run it again to get a second repeat, rerun, the same. It basically looks like with SFT, we're getting similar pass at K, but measurably better match at K. So essentially, we're not really able to reach any new answers that we weren't able to reach before, at least according to this. But we are able to get more consistency in the answers. And ultimately, whether you improve pass at K, pass at 8 or match at 8, you are going to improve what appears to be your performance when you just sample once per question. So improving either one is going to improve your score when you guess once, but you don't really know what the cause of that improvement is unless you separately measure the pass at 8 and the majority at 8. And here we have the answers now. So I've rerun that exact same thing. And pass at 8 is 83% and the majority is 32%. So if I just looked at the mean of 2 runs, and you're seeing here, actually the noise is quite large, I haven't seen noise as much as this, but if we were to just take the mean of these, yeah, it's calculating it for me there. It would be 79 and 34. Which if we compare back to the baseline, it would be 79 and 28. So yeah, I would say it seems like we're in the ballpark of the pass at 8, but we're not, but we are doing better on the majority at 8. So given that, we can move on and take a look at ORPO. And I'll describe a bit how ORPO works. But for that, we're going to first do the run. So let me create a command here. So I'm going to run bash and train on sloth ORPO. We're going to train on the 7,000 rows, or at least the ORPO pairs generated. There's actually 14,000 rows using the thinking tag enforcement. We've got the eval set ready, and this is going to be run 1. So let's run this just quickly before I'm going to check my batch size is okay. I think it probably is because I already ran it. So yeah, that's a good reason. So Unsloth is capable of running ORPO. I will show the differences in ORPO versus SFT. And I will explain some theory around how ORPO works. So here we've very much a similar setup. You can see the longest sequence, 34,000 characters, 16,000 tokens being set there. The model has been printed, but this time, of course, we have not got a system prompt user question and response. We've got it chosen, and then we've got a rejected answer. And now we're up and running. Well, not quite yet. We're actually mapping. The mapping is taking longer because we've got quite a few more. Well, do we have more rows? No, we have the same number of rows, but they're longer to map because they have both the chosen and the rejected responses. And now we're off with training. So if I go over to my tensor board here, I can refresh and I can compare now ORPO. Now, it doesn't really make a lot of sense to show both on the same curves because the loss function is different for ORPO as for SFT. And also there are these metrics around accuracies and margins that are important for ORPO. Now, the basic idea for ORPO is ORPO actually includes SFT, so it includes doing a cross-entropy loss. So the first part of ORPO is actually the same as doing SFT, but it adds in a second term to the loss function that's being minimized. And the second term is based on probability ratios and the ratios between the preferred, the chosen answer, and the rejected answer. So for example, here we have this question and we have a chosen answer, which is this, and we have a rejected answer, which is this. And for what it's worth, it's been rejected, not because the answer is wrong, but because this tag here is wrong. And basically what the second term for ORPO does is it tries to shift the probabilities of the model towards the chosen answer and away from the rejected answer. So if you imagine in kind of 2D, the chosen answer is here, the rejected answer is here, the model is currently somewhere here in the middle. You're trying to shift it towards the chosen answer. And the way you measure how close it's getting to the chosen answer, there are two metrics. One is the accuracy, and the accuracy you want is close to 100%. This means that 100% of the time, the model is preferring the chosen answer over the rejected answer. And the second thing you look at is the margin. And the margin is calculated for the eval and for the train set. I actually need to show it for the eval set. But the margin is kind of the strength with which the model is preferring one model over the other. And the reason that you want to be able to measure the strength is you want the model to have a preference for the right answer, but you want that preference also to be strong. So what we'd like to see is we'd like to see the accuracies going up towards 100, and we'd like to see the margin going up as well for it to convey a stronger margin. Now, when we set up ORPO, the main difference with the script compared to the SFT script is on the formatting function. It's this formatting prompt here. And the difference is that we still put together the system prompt in question and we apply the tokenizer chat template to that. But then we add on, depending on whether it's chosen or rejected, we add on the chosen response or the rejected response and then the EOS token. And what this gives us is it gives us an object that's got not just a single text prompt that includes the completion, it's got the prompt, chosen, and the rejected as well. And the trainer is going to know to look for the chosen and for the rejected, because we will pass this in effectively to the trainer. It's going to know to look for the prompt, the chosen, and the rejected, and to format them correctly. So actually, all you have to do is pass the data set into the trainer. It's been passed in here, but it has to be formatted so it has a column for the prompt, for the chosen, and for the rejected. And it's important that they're formatted with the chat template, which is why I printed this out so you can see exactly what it looks like. Basically, the question looks like this here, and the answer looks like this, with the end of sequence token being added on here, which is important to get the model again to stop. So that's what we have with ORPO. The training seems to be going well. I wonder, do I have time to? Yeah, I have time to talk about the general theory of ORPO. Okay, so I've got this file, and let's talk a bit about three things. So let's talk about supervised fine-tuning. By which I mean just using cross-entropy loss. Let's talk about ORPO, and we're going to call it, let's just talk about ORPO, and then let's talk about GRPO. And we can also talk later about PPO. We can also maybe talk about TRPO. So supervised fine-tuning, easiest way to look at this is some kind of a question like, is Paris the capital of France? And let's consider that we're trying to predict the next token, which is what we are trying to do. So we're trying to predict this. And let's just say that there are three options. There is yes, there is maybe, and there is no. And the language model makes a prediction on a forward pass. And let's say the yes is 40%. Let's say the maybe is 20%. And let's say the no is 40%. So this is doing a single forward pass. I could even write this here. Okay. And now we have the ground truth. And the ground truth just looks like this. It just says yes. So it's just a token that's going to say yes. And so you can think of that as saying 100%. And what cross-entropy does is it's going to look at the difference between what the forward pass prediction was and what the ground truth was. So it's going to look at the difference between yes and yes being 100, and it will penalize it because it's 60% off. And it will also penalize the maybe token and tend to reduce its probability because it is above what it should be according to this sample, which is 0. And the same for no. So the result here is that the yes probability is going to go up if we use cross-entropy, and the probability of these two during backpropagation, the parameters will be adapted in the model to drive these two values down. So that's basically cross-entropy loss. And cross-entropy loss is very robust. It turns out that if you accurately predict the next token, probabilistically, it tends to correspond very well to what we would generally want and correspond to high quality answers. And it's actually kind of hard to beat cross-entropy loss in terms of simplicity for a technique. As you'll see, all of these techniques here end up being quite a bit more complicated. But one of the nice ones, and ORPO, you should know, it kind of derived from a technique called DPO. So if you look through the history of it really is something like, oops, it's printing random things on me, GRPO. The history is something like TRPO, which is trust region policy optimization. And then proximal policy optimization came out of that in 2017. And proximal policy optimization is basically an easier to apply version of TRPO. I'll talk about that in a second. And then GRPO, it's not generalized, it's group relative policy optimization. And this is an even easier way to apply effectively TRPO. So we'll come back to that. But first, let's talk about ORPO, which, by the way, is an easier way to apply PPO as well. DPO, direct policy preference optimization, is a bit like ORPO. So I'll put that in here. It's a bit like DPO, which is direct preference optimization. But here's what ORPO does. ORPO has a loss which is equal to cross-entropy loss plus a factor called beta times some odds ratios. And the odds ratios here are a measure of, effectively, it's the ratios of odds between the predicted, rather the chosen, and the rejected responses. Now, I've said this before, but what ORPO does is it basically tries to minimize the cross-entropy loss, and then it tries to essentially maximize the difference or minimize the similarity between the chosen responses and the rejected responses, which need to be labeled in response or need to be labeled in advance. So this is pretty much how ORPO works. And if you do SFT or ORPO like I'm doing it today, essentially what I'm doing is a version of SFT or ORPO using verified pairs of data, or just verified correct answers. And this is a technique, I don't think using ORPO, but this idea of basically verifying the responses and using the verified ones to include in your dataset, which gives you good quality data. This has been around for some time. It's also been more recently used in the Tulu 3 paper. So that's something else that you can look at. I'm not actually quite sure the exact technique they use, but they certainly use the verification of the dataset in order to get better quality datasets. And if you do this iteratively, then that becomes a form of reinforcement learning. So do this iteratively, and that's of reinforcement learning. Okay, so let's now go to a brief history of reinforcement learning. Actually, I might come back to this in the next video. I want to talk about the history of how these came about and where they brought us to. But I've got the results ready, so I'm going to move on. We've got the ORPO results done at this point. So I'm going to now run an evaluation on this here. So I need to set up a bash command to run Python with the sampling inference script. I'm going to run on the ORPO model, and I'm going to run on this test set here. So let's get that running. And in the meantime, I'll go across to have a look at how TensorBoard performed. So here we have the ORPO results. And what does it look like? Well, the ORPO loss, I'm going to actually hide the SFT because it's not apples to apples because the loss is different. So you can see that's the net log loss. It's falling. The rewards accuracy is a bit bouncy, but they're high. So the accuracy is 85%. That's pretty impressive. But it was high even from the start, so it's maybe making slight improvement. And the reward margin is improving a lot. So we're finding the model is able to put distance between the chosen and the rejected answers, which is pretty good. Now that's on the training side. The accuracies are also doing well on the training side. On the eval side, I actually haven't pinned. So let's look for the rewards margins. Let's pin it. And now that it's pinned, it's here. And yeah, actually the eval rewards margins are improving a lot. I'm pleasantly surprised by that. The training loss is going down, which is good, although it is kind of high, to be honest. I'm a bit surprised with that. And the grad norm is also high. So it's possible we may see bad results, and it may be a case of needing to reduce the learning rate, but the eval loss is falling, so perhaps we are okay. Let's take a look at what happened. So we're running through here, and remember, we're not enforcing the requirement for the format when we're generating evaluations. We're just concerned with whether the answer is correct. So let's see what we've got. And we've got 73 correct, and we've got 32 for the pass at majority. And I'm going to run that once more, just to make sure we have a rerun. And in this rerun case, it looks like, and by the way, no API errors, which is good. We have 77 and 39. So if we look at the average of the two runs, no, that is not the conclusion. We've got about 75 and 35.5. So with these hyperparameters, I would say we're pretty much matching the same performance as the SFT run. I don't think there's a huge statistical difference. You could say maybe the pass at 8 could be a little bit better. Where we are at this point in the study is that we've got an improvement in the majority at 8. We have not been able to get an improvement in the pass at 8. I have a hypothesis that maybe by adjusting my learning rate or hyperparameters around ORPO, I'm able to get towards a better result. I have a hypothesis that this is a clean process, potentially allowing us to run more efficiently than GRPO, although we can directly run a GRPO in a future step, and that's something I'll look at as an ablation. The other ablation that I have coming up, and I have already some experience with, is having the model hold on a second when it hits a wrong answer, and training based on that to see if we can get the model to recover. Now, it's possible that we're not seeing better performance just because of the size of the model, so that's a possibility to keep in mind as well. But it's interesting at least that we are able to get the majority at 8 improvement. That's something that has been shown throughout the years. I think even earlier versions of Llama, it's not something that's new. But I think this will give you some insights into the training of these models and also what is or isn't possible. And so we'll take it from here. If you have any other questions, let me know in the comments and I can maybe integrate them into the next recording. Cheers.